Just turn this in before you leave today, or during the next break. Um, I plan to use the whole time, but we're going to go through a quick intro for the course, and then we're just going to do a review of chemical reactions afterwards. So plan on staying the full 3 hours here. Can you take a look at the course information handout here? Chem 1B, like Chem 1A, is a 5-unit course, so that requires a lot of hours of study, outside class study time. I had one student who cataloged every minute he spent studying chemistry. At the end, actually, I had him for both semesters, 1A and 1B. At the end of 1B, he gave me his compiled list of it was huge. For some homework assignments, he spent, I think, is it 12 hours on, I forgot the exact number, but it's easy to spend a lot of time on homework, right? Because some of the homework problems you could get stumped and it takes you a long time thinking about it. But I have some suggestions. If, you definitely need to spend a lot of time. It takes quite a bit of work to get the material at the level that you have a decent grasp of, and that's what we're shooting for. So plan on spending a lot of hours outside of class. Maybe not 12 hours on one homework assignment or 5 hours. I can't remember exactly what it was. I have it though still. I should take a look at it again. But if you look at the catalog course description, Chem 1B pretty much covers the second half of the general chemistry book. We aren't going to cover every single chapter. There's some chapters that we're going to skip. But there are going to be some major themes associated with those. Unlike Chem 1A, we jump from subject to subject to subject. So, just a whole bunch of different information. In Chem 1B, we focus in on some themes. And one of the themes is chemical equilibrium. Chemical equilibrium, we're going to spend 4 chapters on. And it's just the same type of calculation. What type of calculation is it? It's a stoichiometry calculation, but the stoichiometry is more complicated than the stoichiometry problems you did in Chem 1A. In Chem 1A, you just figured out the limiting reagent, and the limiting reagent's completely consumed. You figure out the theoretical yield of the products, that type of stuff. In Chem 1B, what happens is there are some reactions that only partially react. They don't go to completion. That is, you don't consume all the limiting reagent. There's some limiting reagent left over. And so what do you do in problems like that? Oh, well, you've already encountered it. You encountered them in, for example, weak electrolytes. Like acetic acid. Acetic acid is a weak electrolyte. Weak electrolytes do what? Yeah, they don't completely dissociate, or they partially dissociate, or partially hydrolyze, or partially ionize. That's what we say. And so if I were to ask you, acetic acid, what percentage of it is ionized? Or what percentage of it dissociates? Can you tell me? No, because in Chem 1A, you just said, a little bit, right? Well, in Chem 1B, we want to be much more quantitative. We want to know, well, exactly how much do you expect to ionize? And those are examples of equilibrium stoichiometry calculations. And so we're going to be looking at a lot of different chemical reactions in the context of these equilibria calculations. So I thought I'd start off the semester best with reviewing chemical reactions. And so, looking at some of the other subjects that we cover, when we're dealing with chemical equilibrium, we're looking at driving forces, chemical reactions, that type of stuff. That's covered in chemical thermodynamics. We also have kinetics. Have you heard of kinetics in the probably in intro chem? Kinetics is, motion, but in the context of chemical reactions, it's how fast chemical reactions occur. And they're going to occur at different speeds. Some reactions are very fast and can result in explosions. Other reactions are incredibly slow, and there's no perceptible change over long periods of time. And so there's kinetics and other reaction stuff, including nuclear reactions. Nuclear reactions follow a different set of rules, and we'll look at those at the end. And the course objective here is, this is also from the catalog. We have some student learning outcomes. One is predicting reactions. The other is just wearing your goggles. And we have others as well. But I just list 2 of those here. All right, the prerequisite for this course is Chemistry 1A. You might not have taken 1A here, but if you could just let me know where you had it. I'm just curious. And if you had it here, who you had it with. That's one of the prerequisites. The other prerequisite is math. And so you can just tell me the highest math class you've taken. The required materials for the course, either Volume 2 of Petrucci or if you have the whole book, the complete text is fine. The lab manual is called Catalyst, the Prentice Hall Custom Lab Manual. It's available at the bookstore. 4, a composition book. The composition notebook is going to be your lab notebook. So we have lab manual, item 2. Item 3 I deleted, but I forgot to change the numbers here. So we jumped to item 4. The composition book is just going to be this. If you had Chem 1A from me, it's the same thing, one of these. I prefer quad-ruled, this graph paper. So here's an example of the notebook. These you can buy at the office supply places. If they don't have quad-ruled, you could get, college or wide-ruled. That's acceptable too. If it's not graph paper, I'm not going to hold you strictly to that. If this is all you can find, then just get it. It should be fine. It's just nicer if you have graph paper. It's just easier to make tables, that's all, and graphs. If you want to get it from our bookstore has this. This is in the engineering department, not in the chemistry section. And so this is a research notebook. Basically, it's a bigger version of this, and so there's more space to write. These are only a few dollars at the bookstore, I think. Less than $5 for sure. These are a couple of dollars. So you'll need a lab notebook. Safety goggles from Chem 1A should be fine. A scientific calculator. I recommend a scientific calculator that can solve the quadratic equation. Okay. Officially, graphing calculators are not allowed for Chem 1A and Chem 1B. You have to have one of those SAT-approved scientific calculators. But there are different levels. If you get the cheapest one, it doesn't do quadratics. And so you'll have to buy the more expensive one. The more expensive one's like $15 to $20 version of that. And so just look at the box carefully. I recommend this because we're going to be solving a lot of quadratic equations. If you like solving the quadratic formula and you're good at those and you can solve them quickly, then you don't need it. You could get by with your standard calculator, but boy, it's a pain. It takes a lot of extra time away from other things. And so it's well worth it just to spend and it's always good to have a backup calculator too. And so it's not going to be a complete waste just for this class. Okay, the last item there is a permanent marker, a Sharpie, or similar, for labeling test tubes. We're going to do a lot of chemical reactions this semester, so you're going to have a lot of test tubes to label, keep track of what's reacting, what the products are. Also, when we do chemical reactions, chances of spills and splashes is higher. So a lot of people in Chem 1B, they purchase a lab coat. Lab coats you can get off Amazon. I bought one recently. It was like $15 to $20. A lot of people like 100% cotton, which is good because it's less flammable. But, it still can burn, but they're expensive. So you can get by with some kind of synthetic. Should be all right. Just make sure it's a lab coat. Item 2, nitrile or latex gloves. When I first started using gloves, they were uncomfortable, but after a while you get used to them. And the nitrile gloves are, I think, much better. Nitrile gloves breathe more, so you're less prone to perspiration and things getting slippery. And also nitrile are more chemically resistant. All gloves have a finite lifetime, depending on what chemical you expose them to. Some, gloves are like sponges in a way. And so some gloves just soak up, like acetone. For example, if you're wearing latex gloves with acetone, 5 seconds later, you might as well toss them in the trash because they've already been saturated with acetone, so it just permeates right through. Although acetone's not particularly toxic, I don't really worry about that. But other things, can penetrate those gloves. A nitrile, it depends. Some nitrile are very resistant, but there are some chemicals that go right through it, so they don't last very long. Others that have a hard time, like aqueous solutions, have a hard time getting through nitrile, so you can use those. In fact, you probably can use them more than one day. But they're disposable. They're meant to be thrown away. Okay, if you flip the page over, they're required assignments. You're required to attend both lecture and lab, especially lab. If you miss some lectures, okay, no big deal. But if you miss some labs, that's a big deal. That's a cause for concern. If you do miss lab, you should try to make it up. But if you do miss labs and don't make them up, then there's a chance you could get dropped from the course, even if you're passing the lecture portion. So watch out. Lab attendance is mandatory. All right. If we look at the grade breakdown, exams, quizzes, it depends on, let's say you miss an exam. Well, that's a problem. If you miss an exam, normally there's a penalty associated with that because of the extra time that you have versus other people. And so this is the fairness penalty. It's a 10% penalty, which drops you a grade. And so try not to miss that. It depends on the reason you miss it, though. I'd handle those case by case. Quizzes. The quizzes, sometimes they're announced, sometimes they're not. The quizzes are going to be during the lab period. Homework, we're going to have paper homework, not mastering chem this semester. And so these are just end of chapter problems. You'll just do it in a homework notebook. You could get another one of these books for your homework, or you could do it in loose leaf paper or a spiral bound. For your lab notebook, I definitely want a sewn binding. Sewn binding because you're not meant to tear out any pages. This should be complete. If you do your homework in a notebook, you can turn in the whole notebook. You don't have to tear out the pages. What I'm going to do is I'm going to collect the homework at the beginning of class on a test day. And then after the exam, you'll just take the book with you. And the way the homework is graded, I just grade on how many problems you attempted. I don't check your answers. In fact, I expect all of you to check your answers because the Complete Solutions Guide or the Complete Solutions Manual is available. You can buy that at the bookstore. And so you can check all of your answers there. In fact, you could even copy, you could copy the problems out of the Solutions Guide into your homework notebook and still get full credit. How do I know you copied it? But, a lot of people say don't copy it because you're only hurting yourself. But I figure there are two reasons why it's okay for me. Reason one is it's telling, because if you could just copy the answer out of the solutions guide, write it in here, and get full credit, and you don't do it, that is, let's say you don't do your homework, or you only do a little bit of your homework, then it tells me you don't have time. Maybe maybe you're overextended, but maybe you just don't have the time to put in, because if you can't even just copy the answer, then how long does that take, right? So that's telling reason number one. But the main reason I allow that is because I figure, like that person who spent, I don't know how many hours total on the homework. It's huge. And I have it. I'll bring it in one time so you can see it. But there are some problems that you get stuck on. And so what should you do? If you get stuck on a problem, a lot of instructors say, do not open the solutions guide. Sit there and figure it out. Bang your head against the wall if necessary until you've gotten it. But, after you spend 1 hour, 2 hours, 3 hours thinking about one single problem, is that an effective use of time? No, I think it's a waste of time. You know, at this level of course, and what I mean by this level of course, this is like general chemistry is the base, right? The foundation. There's intro and then general. But being in general chemistry, you're just learning this. You're still like beginners at chemistry. And the best thing I think for beginners at chemistry is not to spend a huge amount of time thinking about one single problem. I think what's better is to take a more of a shotgun approach. A shotgun approach is, you know, try to expose yourself to as many problems as possible. You know, when I transferred to UCLA, I met another student who's doing, I was taking a thermodynamics class, and I was struggling in the class, but the student sitting next to me was doing very well, was top student in the class. And so I started talking to him, you know, because I spent a lot of time. Time wasn't the issue. Whatever it took, I spent every waking minute studying, right? The issue was I wasn't getting anywhere, but this person was at a much higher level. And then I figured it must not be the time. It must be how I was studying. And so I learned from this person. This person was the first person I ever met that did every single homework problem at the end of the chapter. And you think about that, how is that possible? If there are 140 problems, you know, and you spend 10 to 30 minutes per problem, then you don't have enough time. You can't sleep, you can't eat, there's no time. And so what I learned was that person didn't spend a lot of time on particular problems. What they did was, at UCLA, they have the Complete Solutions Guide. And so what they did was they read the problem, and if they figured it out, good. If they couldn't figure it out, well, they thought about it a little bit more, but eventually they just cracked open the Solutions Guide. They cracked open the Solutions Guide and saw how it was done. And so this is learning by example, because if you have a lot of examples and you learn by example, then you'll be exposed to a lot of different problem-solving methods. The problem is if you spend all your time looking at one single problem, and that one single problem has a single pathway to the answer, to the solution, then you only know this one little path. But if you look at every single problem, then you'll see, oh, this is the same as the last problem, but it has an additional twist or an extra step before and after, or this one has 2 extra steps. You know, so a lot of people say that, oh, that test was nothing like the homework. But, you know, the more you look at the homework, you got to look at all the homework, then you'll say, oh, that test was just like the homework. It was just like this problem, except with one extra twist, right? And you don't see that until you get enough exposure to these. And so I think the goal for general chemistry is to expose yourself to as many problems as possible. And so I give you a selected set of homework, but what you should do is, if you have time, look at all the other problems and see what little variations they do in order to get the answer. That way, you know, what happens is then your brain starts to make all the connections. You know, I also was reading about learning and that kind of stuff when I was at UCLA trying to study more effectively. But apparently, you know, your subconscious works at connecting these dots. And then you're able to come up with lots of different pathways for solving problems, right? And so it takes time for this to happen. And what you don't want to do is you don't want to do the homework assignment the night before the exam, because the night before the exam, you do the homework, and there's no way your brain, your subconscious can make these connections to solve more complex problems with more complex pathways. In fact, you want to start the homework early so that, you know, and then you want to expose yourself to a wide variety of different paths, different solutions, this kind of stuff. And then you'll be ready for the exam. You know, sometimes it takes a little bit, takes a little bit of extra time. I have this story I usually tell. I was at UCLA taking a final exam, and one of the problems on the final stumped me, and I couldn't figure it out, and then time was up. And so right after that test, I went to Ralph's to do some shopping, get some snacks and stuff. And then when I was at the checkout line, it clicked. You know, something in my subconscious connected the dots, and then I thought, oh my God, that was so simple. Why couldn't I have gotten it at that time? And it was just one of those things, you know. And so the sooner you get on the homework, the better, because you'll find the exam problems won't be so foreign or so alien. All right, that's the homework. Homework's going to be worth about 10%. There's a late penalty for homework. The late penalty is 50%. And so what you want to do is, even if you didn't complete the assignment, turn as much of it in as possible. That way you can get the maximum credit for that particular assignment. Some people do four problems and say, oh, it's not worth turning in. But to me, it's worth turning in. I mean, 4 full credit points is much better than 2 half credit points or whatever, half credit. And so I know things come up, people get busy, and maybe not able to complete the homework. That's fine, but just make an effort to complete the homework because it shouldn't be difficult. It should be an easy A on the homework. The labs, this semester I'm not accepting any late labs. And so the labs are going to, whether you're finished or not, just turn in what you have. I give partial credit. Late labs, late labs are complicated because I usually wait until all the late labs are in and then grade them. But that doesn't work out so well if they're very late. Okay, the labs are also going to include technique and notebook. Technique is just, are you safety conscious? Do you clean up after yourself? That kind of stuff. And the notebook is, I didn't do this in Chem 1A, but in Chem 1B I'm going to do this. After you collect all your observations, you're going to bring up your notebook and then I'm going to initial it off like this every day in lab. And so I'll take a look at your observations. Let's see what you wrote. The final exam is worth about 20% of the grade. The grade breakdowns, 88 is the cutoff for an A, 78 for a B, 65 for a C. Okay, a note about cheating. Obviously, academic honesty is mandatory. So I keep my eye out. Special needs, if you have any thing you want to discuss, come talk to me. I'll try to accommodate. Okay, any changes are usually going to be announced in lecture or on Piazza. Okay, let's take a look at the syllabus. So you look at the syllabus, when's our first exam? I don't have the exam dates on here. I don't have the exam dates because we're going to do things a little differently than in Chem 1A. In Chem 1A, I had 4 midterms and a final. In Chem 1B, what I'm going to do is I'm going to have individual chapter tests. And so after we finish chapter 15, then the test on chapter 15 will be a week after. At least a week. It'll be on the next lab day. And so if you look at this, we're going to do chemical reactions. And we're going to have an exam on chemical reactions. And so if I finish on Wednesday, then the exam should be January 27th, but I don't like having exams on lecture days because they're short. And so I like having exams on lab days. And so if we finish tomorrow, chemical reactions, then you'll be tested on it on Thursday, January 28th. The way the exams work, these exams are going to be an hour to an hour and a half. They're just 2-page tests. Some people would call them quizzes, but they're worth a lot of points. And so what we'll do is we'll do lab for an hour and a half to 2 hours, and then the test for an hour and a half to an hour on Thursdays. And so the labs, the way I've scheduled it, there's some flexibility there to include. Most of the time we'll have an exam on a Thursday. And so your chemical reactions will be the first one, and then we'll finish, let's say we finish chapter 24 on Thursday. We're only doing 3 sections of chapter 24. We probably aren't going to finish it on Tuesday. We're probably going to finish it on Monday, January 25th. We finish chapter 24 on Monday, January 25th, then your test on chapter 24, sections 1 through 3 will be on February 2nd. That'll be more like a quiz. The point value of the test vary depending on how much material is on there. Or I might combine those two, the reactions and chapter 24. I'll let you know at the end of this week. We finish chapter 15 next week. The following week, we'll have the test, just on chapter 15. The homeworks are going to be due on the exam days. And so your first homework assignment will be chemical reactions. That'll be due on January 28th. Okay, any questions on that? All right, let's take a look at the first homework assignment here. In fact, I'm going to post all your homework assignments on this website. This website's piazza.com. I sent out invitations to most people, but you don't really need the invitation to sign up. To sign up, just click on sign up here. Students. And then you can search the schools. El Camino's in there. El Camino College. And then the class. This class is Chem. In fact, there's only one chemistry class on Piazza. It's Chem 1B. And then you'll need an access code. The access code I wrote on the course info sheet here. But pretty simple. It's just Chem 1B. All lowercase, no spaces. This is it. And then just join as a student. Okay, so now I'm joined into Chem 1B, and then you just add an email address and a password so you can log in. That's it. Okay, once you're in Piazza, then you'll see something like this. So I have the day one handout syllabus, Sylvi, and the course info, a little PDF on chemical risk, and here's your homework. Your first homework assignment is chemical reactions homework. Click on that. Log in, you just enter your email and your password. There are 20 problems here. This homework assignment's worth 10 points, so each one's a half a point. Normally I don't check if you have the right answer, but on this homework set, I'm going to check. Did you get the right answer or not? So let's take a look at the first one, calcium carbonate and sulfuric acid. Calcium carbonate, the formula is CaCO3. If these are a little fuzzy, you should review nomenclature. Sure, because I'm just going to give you the name. I expect you to write the correct formula. Calcium carbonate, what's the state? Is it solid, liquid, gas? AQ. It's solid. Carbonates are insoluble, except for group 1 ammonium. Sulfuric acid, H2SO4, aqueous. And if we react these two together, what forms? Yeah. Calcium sulfate, water, and carbon dioxide. All right, what's the state of calcium sulfate? Solid, liquid, gas, AQ. Sulfates are soluble except for calcium, strontium, barium, silver, mercury, lead. And so this is insoluble. H2O, liquid, CO2, gas. And so this is an example of what type of reaction? Double replacement or acid base, if it's multiple categories. Now, we figure out what the products are, but now we have to come up with a driving force. The driving force is, is this reaction going to occur or not? And so what's going to drive this reaction forward? Gas formation, that's a driving force in double replacement. Or I call these metathesis. We'll talk about that later. But gas formation, we see in it's a neutralization, but so when we talk about neutralization, there are different degrees of neutralization. For example, if you took HCl and sodium hydroxide, you'd form salt water, sodium chloride, and water, which is really neutral. That should have pH 7. But there's another type of neutralization, and another type of neutralization is where you can go from stronger to weaker. So the pH becomes more neutral, but not really neutral. And so this would be an example of that. And so we're going from a stronger, in this case acid, like this, stronger acid, which I'll call SA, to a weaker acid. What's the weaker acid? And so it's kind of neutralizing, but we're still forming something that's acidic. I'm sorry?
It goes to carbonic acid.
Yeah, carbonic acid would be the weak acid. So carbonic acid is a mix of H2O and CO2. This would be the weaker acid. Or we could just say CO2. CO2 is an acid in the normal sense. Do you think of CO2 as being acidic?
No.
No, but it is. It's what we call a Lewis acid. And so really it is the CO2 which is more acidic than water. Sure. And so we're going from stronger acid to weaker acid. Excuse me. So you could label this acid base as well. Anything else? Any other driving force that you look for in double replacement reactions? You look for gas formation, you look for stronger acid, weaker acid, and you look for precipitates. And so here we have a precipitated calcium sulfate. And so can I list precipitation as a driving force as well? Well, this is tricky. This problem is a little bit different, and you probably wouldn't have noticed it unless you've seen a lot of reactions. If you've seen a lot of reactions, you start to notice patterns, like in Chem 4 or Chem 1A. A lot of those reactions, you start off with aqueous, right? In this one, we're starting off with a solid. And so, in essence, we're destroying one, quote, precipitate, quote, and forming a new one. Well, is that really a driving force? And so we're destroying a precipitate, but forming a new one. Should I list precipitation? Well, it depends. You know, and it depends because all driving forces have something in common. When we think about driving forces, what do they all have in common? We're going from this to this always. In any driving force we look at, whether it's gas formation, stronger acid, the weaker acid, or precipitation, we're going from this to this. Yeah, stability, right? And so we're going from things that are less stable to things that are more stable. So typically, yeah, precipitates are more stable. You know, carbonic acid, CO2 is more stable, less reactive than sulfuric acid. You know, right? You wouldn't worry too much about inhaling some CO2, but you would worry about inhaling some sulfuric acid, probably. Right? And so we think in terms of stability. And so in Chem 1B, we're going to have this type of problem occur where, you know, is this really a driving force? Well, it depends. Which one is more stable, calcium sulfate or calcium carbonate? And so what kinds of clues can I get in terms of stability? Which one is a more stable solid?
Their oxidations.
Well, the oxidation states might or might not tell you. You know, calcium, we have calcium 2 plus, carbonate, we have CO3 2 minus. And we can look at the oxidation states within those. But we look at over here, we have calcium 2 plus, and then sulfates is SO4 2 minus. So in certain ways, they look similar. You know, carbonate, do you know what the geometry of carbonate is? Molecular geometry, the carbonate ion? Not tetrahedral. You guys are trigonal planar. Carbonate's trigonal planar, so it's triangular plane. Sulfate is tetrahedral. And so in an ionic lattice, it might be harder to pack in carbonate ions because of their shape than sulfate ions. You know, sulfate ions should be a... Yeah, but what do we look for in terms of stability? How could you tell which solid is more stable? Calcium carbonate or calcium sulfate? One thing is we might look at things like oxidation state. I'm not looking at chemical reactivity here. I'm just looking at, you know, the physical stability of calcium sulfate and the stability of calcium carbonate, not what they can potentially react, because the reaction's here as written. So we're looking at which precipitates more stable. And looking at which precipitates more stable, we might think in terms of what? Bonding, right. We think in terms of bonding. And so what forms stronger bonds? Calcium and carbonate or calcium and sulfate? And so there we think about the size and packing these together in a lattice and that kind of stuff. And so then we start thinking about lattice energies. Do you guys remember lattice energies a little bit? Yeah. You know, which one has a higher lattice energy? That is, which one is a stronger lattice? Which lattice is harder to break apart? And that has to do with bonding. And so we can get some clues there, but in terms of lattice energies, we like to think in terms of charges and this type of stuff and how they pack together, but we don't have that information. And so we start to think about other things as well. And the other things that we start to think about are maybe some of the factual data on calcium carbonate and calcium sulfate. And this factual data is just experimental data that might be collected. So for example, melting points. If we look at the melting points, the one with the higher melting point should be more stable or less stable? More stable. Higher melting point, it requires more energy, more heat to break it apart. And so we could look at the melting points, but do you know the melting points? Could you figure out the melting points by looking at the ions, the charges, the shapes, this kind of stuff? Well, in theory you could, you know, you could use theoretical chemistry to try to figure it out what the melting point is, but that's too difficult for us. And so the easiest thing to do is we look it up. You could look up the melting points. You know, before there was Wikipedia, we would look up the melting points in something called the CRC, Handbook of Chemistry and Physics. This is a big, thick book, a whole bunch of melting points. Not only does it have melting points, but it also has solubilities. So for example, if we're looking at which one's more stable, and this is probably more practical for us, we would ask ourselves, which one is less soluble? Because the less soluble one is more stable. And so we could look at it based on some experimental data, which of these two has the lower solubility, and that should be the favored one. But when we're doing chemical reactions, all we need is one driving force, right? One driving force, and then it should go. And so we have it. We have the gas formation, and we have the stronger acid, the weaker acid. The precipitate, we don't know unless we look it up, right? Because it's too difficult to figure it out. Just at a glance. Okay, so this reaction should go. This is what we call the complete equation, or I call the complete equation, CE. I also want the ionic equation and the net ionic equation. And so let's go ahead and finish that here. And so this is a question mark. This precipitation might be a driving force, it might not. I don't know, but it's okay because we have the other stuff driving it. Now, when I come up with the ionic equation, what do I do? Yeah, we split apart. Do we split apart calcium carbonate? No. In fact, we only split apart what? Solutions? Solutions that dissociate? But we call those something. The strong electrolytes, right. We only split apart the strong electrolytes. Strong electrolytes are strong acids, strong bases, and the soluble salts. Calcium carbonate is an insoluble salt, so we don't split that apart. Sulfuric acid is a strong acid, we split that apart. What does it split apart into? Does it split apart into 2H plus and a sulfate? Yes? I'm sorry. What was it? Oh, H3O. Okay. For us, initially we aren't going to use H3O plus. We're going to take H plus as being H3O plus. This is a shorthand way. H plus doesn't really exist. H plus is just a single proton. Single protons are just too reactive to exist in water. But, you know, it just saves time not having to write H3O plus. H3O plus is more accurate. It's good. But for right now, I'm going to ignore it. This means the same thing. And so we don't write this. What do we write? Yeah, this is going to be H plus plus HSO4 minus. Because normally when an acid reacts, you know, it doesn't lose both protons simultaneously, you know, in the same instant of time. What happens is a base comes over and plucks one proton off, the base being water in this case, and then it tries to pluck the second proton off. But after it plucks the first proton off, then we're left with HSO4 minus. But is HSO4 minus a strong acid? HSO4 minus. No, HSO4 minus is a weak acid. And so that second proton doesn't completely split off. And so sulfuric acid in water just ionizes or hydrolyzes to H plus and HSO4 minus, and that's it. These are the major species in solution. This is going to go to calcium sulfate. Calcium sulfate is an insoluble salt, so we just leave it. Water is a non-electrolyte. CO2 is a non-electrolyte too. And so this is it. And then we look for spectators. Are there any spectators here? No. And so the ionic equation and the net ionic equation are the same thing. And so this is what I want you to do for your homework. You know, if it's a double replacement type reaction like this, you'd write out the complete equation, the ionic equation, the net ionic, and then you tell me what the driving force is. But not all the reactions are going to be double replacement style reactions. We're going to have other reactions as well. The other reactions, we don't necessarily do this. The other reactions, we might just end up writing the ionic or net ionic equation for. So you can see some of these here. There are actually quite a lot of reactions, so it'll take some time to go through. So for the chemical reactions review, I'm just going to do these via PowerPoint here. First, we're just going to talk about chemical reactions in general, and then we're going to look at specific types of chemical reactions. And so looking at chemistry, what's a dictionary definition of chemistry? Dictionary definition is the science of the composition, structure, properties, and reactions of matter, especially of atomic and molecular systems. Well, when I look at this, yeah, that sounds good, except as a chemist, I would change things a little bit. So what would I change? I change this. It says the science of the composition, that's fine. Structure, that's fine. Properties and reactions, well, that's what I would change. Because the dictionary definition is defining properties as physical properties and reactions as chemical properties. What I would just say is, it's the science of the composition, structure, and properties of matter. That's what chemistry is. The science of the composition, structure, and properties. And we all know that there are two types of properties. We have physical properties and we have chemical properties. And so this is what chemists do all the time. Chemists are always thinking, about properties and how properties relate to composition and structure. For example, diamond and graphite are both, they both have the same composition. They're both made out of carbon, but what makes their properties so different? Well, it's the structure. Diamond's all sp3 carbons, graphite's all sp2 carbons, right? That type of thing. And so this is what chemists are doing all the time. And so when I think about chemistry, I think of chemistry in this way. It's understanding the properties of matter based on composition and structure. And so what do we do? Well, I'll tell you what we do. We spend a lot of time thinking about how the composition and structure affect or influence properties and how the properties arise from composition and structure. But that can be quite complex because here, we kind of know what the structure of calcium carbonate is. If you draw out the Lewis structure of calcium carbonate, you could draw it out. Calcium ion, carbonate ion. And we know in 3D lattices, we're just going to have a whole bunch of these ions arranged in some kind of lattice structure. But, how does knowing this help us here? Well, depends on how much detail we have. And so, typically, as chemists, we approach this via two methods. One is we approach it theoretically, look at oxidation states, look at the structure, look at this. But oftentimes we aren't going to be able to get enough information, and therefore we always can fall back on what I call descriptive or experimental fact. And so over here we're trying to figure out which one's more stable, calcium carbonate or calcium sulfate, and we're trying to do it in a kind of a theoretical approach using our ideas of structure and charge and this kind of stuff. But in the end, that didn't get us anywhere. In the end, what we had to do is we just had to go to some experimental fact that somebody measured, the solubility. And that's easy to measure. Somebody measured how many grams of it dissolved in, let's say, 100 milliliters or a liter. And so that's exactly what we're going to do. It makes me cringe sometimes to think, that people say, you shouldn't memorize. Don't memorize. Memorization is not necessary. To me, memorization is so important because if you don't have a lot of factual knowledge memorized, then you can't really apply any theoretical. And definitely, if you have no factual context, then there's nothing you can do with the theoretical. Because theory, at least the theory underlying chemistry, is very difficult, right? For example, is HCl a gas, liquid, or solid? Pure HCl. That's easy. What is pure HCl? It's a gas. Why? You memorized it, right? You memorized that. Well, what if you didn't memorize that? If you didn't memorize that and somebody asks you, prove, give me a mathematical proof or whatever, theoretical proof that HCl is a gas at room temperature, how are you going to prove that to me, theoretically? Well, I guess you could if you knew, theory well enough and you could do the math, but it's just too much work, right? And so this is why we have this two-pronged approach. The two-pronged approach is both the theoretical. It's not that we ignore theory. Of course, we want to use theory as much as possible because theory, the more theory we know, the less we have to do in lab because we could just predict what's going to happen. This is kind of interesting because there are lots and lots of examples, but one example that's more current is the hunt for the blue LED. The green LED has been known for a long time, and the red LED probably even longer. And so they knew the green LED, the red LED, all that was missing was the blue LED because red, green, and blue make all the colors in the rainbow. With only red and green, you can't make all the colors. You can make, yellow and some other colors, different shades. And so there are basically two groups in the race for the blue LED. You had your theoreticians, and theoreticians were using computer modeling and theoretical knowledge to figure out, what band gap, and how to get that band gap using what elements, right? And they wanted to predict this theoretically. And so they're doing these computations, and then they test. They say, okay, this mixture should make the blue LED. And so they get somebody to make it, and then test it and see if it worked. Well, it didn't initially. And then you had the experimental chemists, the synthetic, not chemists, but engineers and whoever else, just mixing different things. They kind of had a target because they knew some theoretical stuff, but they just mixed it and see what happens. And you think, wow, with an approach like that, it's going to take a long time to find it because you're just taking these random, seemingly random, but not totally random mixtures and seeing if it works. And do you know who won the race to the blue LED? It was the experimental. Right? And that guy got the PhD. I mean, not the PhD, the Nobel Prize in physics. Excuse me. He's currently at UCSB. And so we do this all the time. We use a mix of theory and descriptive chemistry in understanding science. Okay, when we use this mix, then we want to apply it to things. And so what are some of the things we apply it to? Well, first, we kind of build up some little factual database structure and properties. And the factual database might be like graphite and diamond. Based on the different structures, we get huge differences in properties. And so we look at each substance. Each substance has a unique set of chemical and physical properties that arise from its composition structure. So we look at different substances and look at that and get some kind of framework or reference frame so that we can do this. We could use composition and structure to determine the properties. So if we know, a little bit of the composition, calcium carbonate, we know a little bit of the structure, then we can infer certain things about the properties. We can do this for carbon, but let's say we do this for HCl. Well, what's the structure of HCl? Well, HCl occurs as molecules, diatomic molecules. Composition, hydrogen and chlorine. It's a gas. And so what types of properties can we determine? Well, HCl is a gas. I have that memorized. HCl is a gas, so it has fairly low density. All gases have low densities, mostly empty space. HCl, if it's a gas, it must have a very low boiling point, a very low melting point. Otherwise, it wouldn't be a gas room temperature. Those types of things. And so we could look at some of the physical properties, density, color, this type of stuff. Solubility. Is solubility a physical property or chemical property? It's a physical property. So HCl dissolves in polar liquids like water, etc. It'd be pretty insoluble in nonpolar liquids. And so those are some of the physical properties. Now, what we want to do is we want to look at the structure and then determine some of the chemical properties of HCl. And so we'll take a break here, and then we'll talk about the chemical properties of HCl next based on its structure and composition.